Welcome back. This video provides a tutorial introduction to R. Before we get started, you'll need to do two things. First, go to this link you see here, the R homepage. This page gives a little background about R, which was developed in the 80s as an open source alternative to the S language developed at Bell Labs. Click on CRAN. CRAN is the Comprehensive R Archive Network, which is the official download site for R and R packages. Once you're here, you'll be asked to select a mirror site. I usually select something near me geographically. Any of these will be reliable and safe. After you install R, go to the RStudio site that you see here and download RStudio Desktop, the free version here. RStudio is a beautiful IDE that supports R coding. After you've installed R and then RStudio in that order, open up RStudio and we'll get started. When you open RStudio, you'll see these three panes. On the left, we have the console, which first prints out some information about our R version, in this case 4.0. To clear the console, we can hit Ctrl-L. On the right, we see two smaller panes. The top pane we use to look at our data, and the bottom pane we use to look at plots, help, and so forth. I'm going to be following along in Chapter 2 of the book. You can find the PDF of the chapter at karenmazziti.blogspot.com. R is an interpreted language, which means that we can get to know it by playing around at the console. Let's type in an expression. So you see it has the usual order of operations as other languages. When you type in an expression, R returns the evaluation, which in this case was 3. But what is that 1 doing there? The 1 is just telling you that your result is a one-dimensional object. It's a vector of length 1. Think of everything in R as being an object. We don't really have scalars in R, so this 3 is actually a vector of length 1. Alright, even though we did something, our environment over here is still empty. That's because we didn't save our result to a variable. So I'm just going to call it x. And notice that the assignment operator in R is less than dash. And it's actually bidirectional. You can use the equal sign, but this operator is more commonly used. Now I have something in memory. I have a variable x, and it has the value 3. In our environment pane, x looks like an integer, but we can check what type of a thing it is with the built-in typeof function. And we see that it's a double. So numbers are stored as doubles by default. If you really want to store an integer, you can use the L indicator. For example, we can say x is 1, 2, and 3. And we see now that x is now an integer vector with 3 values. And so let's try the typeof again. By the way, the up arrow works just the same as in Unix to get previous commands. Now we see the type of x is an integer. What this also displayed is that R is dynamically typed. So an identifier like x is actually just a pointer to an object. And if you change the thing that it's pointing to, it changes essentially its type. A vector in R is a sequence of objects of the same type. And the C function will combine objects into a vector. Let's see what happens when we combine objects of different types. So let's combine an integer, a floating point, and let's say a character. And then check the type. We see that it's going to be of type character because it will coerce everything in the vector to be of the most inclusive type. Another way we can create a vector is with the sequence operator, which is the colon. So x is now a vector of the numbers 1 through 10. Look what happens when I say x times 5. Notice that it multiplied every element in the vector by 5. Normally we'd have to write a loop to get this behavior. R also has a lot of built-in statistical functions like sum, and you may be wondering why it's 55. That seems low, and the reason is we didn't save this value back to x. In addition to the sum function, we have min, max, range, mean, and median. We've seen integer and floating point vectors. Let's make a logical vector. Let's just say x greater than 5, and now we have a true-false logical vector. If we sum that, we see that we get 5 because there were 5 true values. So 0 is false and true is 1. Let me type this syntax and then explain it. This first part with the brackets will select all elements of x that are less than 5, and then this part on the right will replace them with 0, as we see here. Here I've cleared my screen and then made x a vector from 1 to 10 again. And then I indexed with square brackets x sub 1. It's 1. What this means is that R starts indexing at 1, not 0 like every other language. Notice also that if you index out of bounds, you don't get an exception. It appears to be using x sub 0 for some information about the vector, and if you index beyond the end of the vector, you just get NA. An R list is a sequence of objects that don't have to be of the same type, and lists can contain other lists as elements. In this first line, I have created a list with the built-in list function, and notice they are of different types. When we index into lists, we use double square brackets. The length function works on both lists and vectors, and many other data types. A matrix is a 2D object with elements of the same type. And an array is like a matrix but can have more than 2 dimensions. In this first line, I created a matrix of the numbers 1 through 10 and specified that it would have 2 rows. When I echo back out the matrix, notice we have these handy hints here on how to index. The indices are in row-column order, so M23 is row 2, column 3. A data frame is a 2-dimensional structure where each column can be of a different type. Most of the time we'll read in a data frame, but we can construct them manually. Here I've constructed 3 vectors, an integer vector of x, y is a floating point vector, z is a character vector, and then I've combined the columns with the cbind operator and then converted it to a data frame. When I echo out the data frame, we see that we have 3 rows and each column is of a different type. We can access a given column with the dollar operator. So df $x gives us the first column. We can also change the column names if we don't like those. And we could say the first one maybe is a ticket, the second one is a discount, and third is maybe section. In RStudio, you can change your default directory in the menu options, but you can also do it programmatically. getWD returns your default directory and setWD sets it. Read.csv is used to read in a data frame, and if we want to take a quick look at it, we use the str for structure command. We see that it has 1309 observations, that's rows, and 14 variables, that's the columns. And it lists each column and the starting values here. We'll look more at data frames later in this video. We can see everything that we have in memory over here in the environment pane. We can also list it at the console. If we want to just clear the slate and remove everything, we can remove with this syntax. And now we have nothing there. R has a lot of built-in data sets. We can get a list of those by just typing data at the console. As you can see, there are many, many data sets. I'm going to X out of that. To bring a data set into working memory, you use the data function. And to find out more about it, you can use ? air quality. And what we see is that this data frame has 153 rows and 6 variables, and it has to do with air quality measurements in New York, May to September 1973. I don't want to keep typing air quality, so what I'm going to do is make a copy of it and call it DF, and then I'm going to remove air quality so I don't have 2 of those in memory. Before we do any machine learning with data, we want to spend some time in data exploration. Fortunately, R has a lot of built-in functions for data exploration. There are head and tail functions, where you can specify the number of rows you want to look at. Dim gives you the dimensions of the data frame. We've looked at structure before. And there's also summary, which will give you statistical information on each column. Notice in the output of the str function that there were a lot of NAs. NAs are missing values, and they can cause problems for many algorithms. First, we need to quantify how many NAs that we have. I'm going to clear my screen again. Our functions tend to nest inside of each other, and so you have to kind of read them inside out. So the isNA function applied to just one column, one vector, ozone, is going to return a binary true-false vector. If we sum those, all those that are true, we see that we have 37 NAs in that one column. And we see here a problem that NA can cause. When we try to take the mean of that column, we get result equals NA because there's NAs in that column. What we can do though is add an extra parameter, which tells it to ignore the NAs. A trickier problem is deciding what to do with these NAs before we do machine learning on them. One thing that we can do is find the mean, and I'll save it somewhere. So I'll save it in variable m for the DF ozone column. What we're going to do is select all of those that are NA, and we're going to replace those with our mean. Now when we take the mean of ozone, we see that we get an actual number there. In addition to exploring our data with functions, we also want to explore it visually. Let's look at a few built-in plots we could try. We could try a histogram, let's say of temperature. And let me rearrange this so I get a little bit better look at that. Let's try a plot of the same column. And we get a scatter plot here. We can also use the plot function for xy. So let's plot temperature on the x-axis and then ozone on the y-axis. And what we see here is a slightly linear trend, although it's very messy, but it does seem that as temperature increases, ozone increases as well. Here I've added some extra parameters to the plot function to change the shape of the dot, the color, and the size, and to add some labels. And we see the new plot here. One reason this plot is very messy is that we replace the NAs with a mean value, and you can kind of see that in this horizontal line here. Often we want to know if there are correlations between variables. In other words, are they both going up, or is one going down as the other one goes up? Correlation ranges from +1 to -1. Correlations that are near positive or -1 show strong positive or negative correlations, while correlations near 0 show no correlations between the variables. In this first line, I've used the built-in correlation function on just the first 4 variables, and I've said use equals complete to ignore the NAs. We can also get a visual representation, which we see down here in the plot area, with the pairs function. Looking at these, you see a little bit of a negative correlation here between wind and temperature, and maybe slightly between wind and ozone. In this first instruction, I created a new column just by saying $$ and the name, and I've assigned every element to be false. Then I selected only those elements where the corresponding temperature column was greater than 89 and set those to true. And then I converted the column to a factor. A factor is a qualitative variable in R. If we redo the str function, we see our new column here and that it is a factor with 2 levels. Factors are represented internally as integers and also have a character representation. When we plot the new column, we see the distribution. Most days were not hot, a few were. Most of the time we won't be working at the console. We'll be using an R notebook. The notebook intersperses commentary with code. To create a notebook in RStudio, go to File, then New File, then R Notebook. You'll see this boilerplate code here. At the top we see the YAML code that will render into a heading. We could also add an author line. The white portions are text in Markdown. If you click the Help menu and then Markdown Quick Reference, you'll see a nice cheat sheet here for Markdown. Markdown is popular because it lets you format as you type without taking your hands off the keyboard. We see here is an example of how to create a hyperlink. When you have single asterisk around text, it's italics. Double asterisk would be bold. Code chunks appear in gray. This code will actually be executed when the notebook is rendered, or knit as we say, with the preview button up here. You should read through the boilerplate down below the code chunk because it tells you how to add new code chunks, which differs on Mac and Windows. Let's render this into HTML by clicking this button. Notice that we can knit it to either HTML, PDF, or Word. I'll hit the HTML button. We see the rendering over here in this pane, and we could show in a new window if we click this button. Let me resize the windows so we can get a better look at how the Markdown rendered. Here we see the hyperlink that we created with this Markdown, and notice our YAML code up here rendered into this heading. The code chunks will display, and any output they produce will display immediately below the code chunk. Notebooks end in .rmd. In RStudio, we can also create R scripts. These are plain code files that end in .r. The reason that notebooks are popular is that you can surround code chunks with explanatory material, which makes notebooks great for sharing ideas. In the next video, we'll look at R control structures. You can download the notebook we'll look at from the GitHub and follow along. Until then, I recommend you play around with R at the console.